A solid cylinder known as surface 2 is located at the center of a hollow sphere which is considered as surface 1. The diameter of the sphere is 1 meter, while the cylinder has a diameter and a length of 0.5 meter each. The radiation configuration factor or shape factor F11 is A 0.375, 0.625, 0.75 D1. The solution to this could be given as: a solid cylinder is located at the center of a hollow sphere. Sphere is 1. A solid cylinder, which is surface 2, diameter and length both are equal, that is equal to the 0.1. D is equal to L is equal to 0.5 meters, whereas the sphere is radius is 0.5 meters. Now, considering the inside surface as 2 and surface of the sphere as 1, here there are two surfaces involved in the problem. Therefore, I can write here as F11 plus F12 is equal to 1. But F21 is equal to 1. Why? Since 2 is totally surrounded by 1. Therefore, the shape factor of the inner surface, that is 2, with respect to the outer, that is 1, is 1. From reciprocity relation, A1 F12 is equal to A2 F21. What is A1? 4 pi radius of the sphere square into F12 is equal to, what is A2? Surface area of the cylinder, that is pi dl plus pi by 4 d square into 2. That is the total surface area of the inner cylinder into, what is F21? That is 1. Implies F12 is equal to pi into, what is d into L? D is 0.5, L is also 0.5 plus pi by 4 d square is 0.5 whole square into 2 whole divided by 4 pi. What is radius of the sphere? Half of 1, that is. So we will get F12 here. After getting F12, what is F11? Implies shape factor of the inner surface of the sphere, shape factor of sphere with respect to itself is equal to 1 minus f12. Hence the answer. You will get one of the answers here. So, by knowing the shape factor of the inner cylinder with respect to the outer sphere as 1, we had calculated shape factor of 1 with respect to 2. Having known f1 to 2, we could calculate f11. Hence the problem. Now I shall solve a problem given in gate 99. In a pulverized fuel-fired large power boiler, the heat transferred from the burning fuel to the walls of the furnace is A. By conduction only. By convection only. C. By conduction and convection. D. Predominantly by radiation. Here the answer should be predominantly by radiation. The reason is, in a pulverized fuel large power boiler, there is a huge temperature difference between the flue gases and the walls of the furnace. So, very large temperature difference automatically make the radiation heat transfer to dominate completely over the conduction and convection. Whenever I said already, whenever the temperature difference is higher, radiation heat transfer dominates over conduction and convection. The reason is, radiation heat transfer is proportional to the difference of the T power force, temperature to the power of 4. Therefore, at a higher temperature, the fourth power of this absolute temperature becomes very huge. Hence, radiation dominates over conduction and convection. Answer is D. Predominantly by radiation. Whenever the temperature difference is large, radiation dominates over conduction and convection. Now I shall solve a problem given in gate 2002. What is the value of the view factor for two inclined flat plates having a common edge of equal width with an angle of 20 degrees. A 0.83, 1.17, 0.66, 1.34. It is like this. The two plates having common edges, common edge of equal width, this is 20 degrees. If this is 1, this is 2. shape factor cannot be greater than 1. 1.17 and 1.34 they are ruled out. So the choice is between 0.83 and 0.66. Because the angle being very low, they have a considerably more shape factor, that is A. For example, if you take two square plates kept like this of equal size, all sizes are equal, then shape factor of 1 with respect to F122 is 0.2. So as this is for the inclination of 90 degrees. Here the inclination is only 20 degrees. They are being very close to each other. Shape factor will be almost equal to 1, that is 0.83. Now I shall deal with the radiation shields. Consider two large parallel gray surfaces. This is 1, this is 2, epsilon 1, epsilon 2, T1 Kelvin, T2 Kelvin. Now the thermal circuit or radiation network for the problem will have three resistances. Two surface resistances and one space resistance. This is EB1, this is EB2. So Q net radiation heat transfer is equal to EB1 minus EB2 by sum of all the resistances 1 by epsilon 1 plus 1 by epsilon 2 minus 1 per unit area. Because here A1 is taken as A2 is taken as 1 meter square, F12 is equal to F21 is equal to 1. Now we know this radiation heat exchange where T1 Kelvin and T2 Kelvin are the absolute temperature of the two plane surfaces and epsilon 1 and epsilon 2 are the emissivities of the two surfaces. Because they are very large surfaces, shape factor with respect to each other will become 1. Now we want to reduce the heat transfer rate between these two surfaces. So then what I do is I introduce a shield like this. So this is the figure which indicates the presence of the shield between the two surfaces, epsilon 1, epsilon 2. The shield has emissivity of epsilon 3. Emissivity of radiation shield. T1 Kelvin, T2 Kelvin are the temperatures of the two gray surfaces. The shield has got emissivity of epsilon 3. Now, the radiation network for this heat exchange between surface 1 and surface 2, 3 is taken as the shield. The radiation heat transfer between 1 and 2 will have totally 6 resistances between the two surfaces, out of which 4 are surface resistances, 2 are space resistances. Now the radiation network for this heat exchange with shield is given as the radiation network has got 6 resistances. EB1, EB2. First resistance is surface resistance of the surface 1. Then space resistance between 1 and 3, that is 1 by A1 F13, 3 is the shield. Then we will have the surface resistance of the shield. Then we will have the again surface resistance on the other side of the shield. Looking at surface 2. Then we have the space resistance between 3 and 2, A3, F32. Lastly, we will have the surface resistance of 2. So totally there are 6 resistances, out of which 4 are surface resistances and 2 are space resistances. Here, because they are very large surfaces, A1 is equal to A3 is equal to A2 is equal to 1 meter square, and also F123 is equal to 1 and F322 is also equal to 1. Because they are very large parallel surfaces, all the shape factor with respect to each other become unity. Now the radiation heat transfer rate between 1 and 2 with shield between them is equal to Q122 with shield is equal to EB1 minus EB2 divided by sum of all the resistances. That results in sigma T1 power 4 minus T to the power of 4 divided by 1 minus epsilon 1 by epsilon 1 A1 plus 1 by A1 F13 plus 1 by epsilon 3 by epsilon 3 A3 plus 1 minus epsilon 3 by epsilon 3 A3 plus 1 by A3 F32 plus 1 minus epsilon 2 by epsilon 2 A2. That is considered as here A1 is A3 is A2 is equal to A1 is A3 is A2 is 1 meter square. So putting the values of A1 is equal to A3 is equal to A2 as 1, we get 1 by epsilon 1 minus 1 by 1 plus 1 by 1 into 1 plus 1 minus epsilon 3 by minus 1 by 1 plus 1 minus epsilon 3 minus 1 by 1 plus 1 by 1 plus 1 by epsilon 2 minus 1 by 1. So this results in the sigma T1 power 4 minus T to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 3. I'm sorry, 2 by epsilon 3 plus 1 by epsilon 2 minus it becomes minus 1 it becomes minus 2. So this results in if all emissivities are equal, that is epsilon 1 is epsilon 3 is epsilon 2 is equal to epsilon, then Q122 with shield is equal to 4 by epsilon minus 2. But Q without shield with all emissivities with all epsilons equal without shield, it results in sigma T1 power 4 minus T to the power of 4 divided by 2 by epsilon minus 1. Comparing the above equations, we get Q with the shield is equal to 1 by n plus 1 into Q without shield, where N is equal to number of shields, because sigma, this can be written as 2 into 2 by epsilon minus 1. So when we keep one shield between the two surfaces, the reduction in heat transfer rate is by 50%. That is, with one shield kept between the surfaces, the heat transfer rate reduces by 50%, provided all epsilons are equal. Provided all epsilons emissivity values are equal. The note here is, if thermal radiation heat transfer rate is to be reduced by 75%, then keep three number of shields having same emissivity as that of the two surfaces exchanging heat. If we keep two shields, then the radiation heat transfer rate will reduce by 66.6%, because Q with shields is equal to 1 by n plus 1 Q without shields, where n is the number of shields kept. Now I shall do a small problem on radiation shields. The problem is given like this: two very large parallel planes with emissivities 0.3 and 0.8 exchange heat. Find the percentage reduction in heat transfer when a polished aluminum radiation shield with emissivity 0.04 is placed between them. The solution could be given like this: the heat transfer without the shield is given by Q by A without sigma T1 power 4 minus T to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. This results in 0.279 sigma T1 power 4 minus T to the power of 4. Now, with the shield, the radiation network is given as, we'll be having 6 resistances, 1 minus epsilon 1 by epsilon 1, taking all the areas. A1 is A3 is A2. 3 is shield. All areas are equal to 1 meter square. All areas are equal to 1 meter square. So I'm not writing the areas in the circuit. 1 by F13. 3 is shield here. This is surface, this is shield, this is surface. 3 is shield, surfaces are 1 and 2. EB1, EB2. 1 minus epsilon 3 by epsilon 3, 1 minus epsilon 3 by epsilon 3, 1 by A3, that is 1 F32 minus 1 minus epsilon 2 by epsilon 2. Now I calculate individually the resistances. 1 minus 0.3 by 0.3, this is 2.33. 1 minus epsilon 3 by epsilon 3, this is 1 minus 0.04 divided by 0.04, this is 24. 1 minus epsilon 2 by epsilon 2, this is 1 minus 0.8 by 0.8, it results in 0.25. So the total resistance with the shields, with one shield, is 2.33 plus 2 into 24 plus 2 into 1 surface space resistance plus 0.25. It results in 52.58. Therefore, Q by A with the shield is sigma T1 power 4 minus T to the power of 4 divided by 52.583. This results in 0.019 sigma T1 power 4 minus T to the power of 4. So earlier we got it as 0.279, now we got it as 0.019. The percentage reduction in heat transfer rate is 93%. The heat transfer rate has reduced by 93.2%, having one shield of aluminum, made of aluminum. Here we could note that whenever we are keeping a shield, always keep the shield having preferably low value of emissivity. Then that will give it to the more resistances offered by the more surface resistances offered by the shield. Please note that the shield is offering 2 surface resistances. When we are keeping a shield having low emissivity or high reflectivity, I can say, that is the reason why in this problem we have kept a highly polished aluminum shield having more reflectivity or very low emissivity. That will put up higher surface resistances in the circuit, thereby radiation heat transfer will get reduced to a greater extent. Please note that here the heat transfer rate is reduced by 93.2% just by keeping one shield having very low emissivity or very high reflectivity. Hence the problem.